Hi, my name is Sushma. For survey research on real-time operating systems, I have chosen the topic free RTOS. As an introduction, we are going to talk about operating systems, real-time operating system, and free RTOS. An operating system or OS is software that manages computers' hardware and provides services to applications. A real-time operating system is a type of operating system that is designed to process data and respond to events within strict time constraints. RTOS is crucial in systems where time is critical, like in embedded systems, industrial controls, or automotive electronics. Free RTOS is widely used open source RTOS designed for microcontrollers and small embedded devices. It is lightweight, efficient, and support multitasking, making it ideal for real-time applications in IoT and automation. So what is operating system? An operating system or OS is essential software that manages both hardware and software. It acts as a bridge between user and the computer's hardware, ensuring efficient operation. The OS performs several core functions like managing processes, allocating memory, handling files, and managing input or output devices. Security is also a major function, protecting systems integrity and user data. There are various types of OS depending upon the application. There are batch OS for group tasks, time sharing OS for multi user systems, distributed OS for coordinated multi system, and embedded OS for specialized hardwares. A real time OS, which we are going to focus more. The common examples of operating system include Windows, Linux, Mac OS, Android, and iOS. What is real-time operating system? A real-time operating system or RTOS is designed to handle tasks within strict time constraints, making sure responses are fast and predictable. It's especially important in systems like medical devices, automotive controls, and industrial automation where delays can be critical. RTOS offers deterministic behavior, meaning tasks are completed exactly when expected. It uses priority based scheduling so urgent tasks can preempt others. This ensures low latency and reliable performance. There are three different types of RTOS: hard RTOS, soft RTOS, and firm RTOS. In hard RTOS, missing a deadline causes system failure, whereas in soft RTOS, some missed deadlines are okay but not ideal. In firm RTOS, occasional misses reduces the performance but do not crash the system. Popular RTOS examples include FreeRTOS, VxWorks, RT and QNX. Let's talk about FreeRTOS. FreeRTOS is an open source real-time operating system originally developed by Real-Time Engineers Limited and is now maintained by AWS. It's specially designed for microcontrollers, so it has a lightweight footprint perfect for resource-constrained devices. FreeRTOS includes a real-time kernel and essential libraries that support features like connectivity, security, and over-the-air updates. It supports both preemptive and cooperative multitasking, allowing developers to choose the best task management approach for their application. With priority based scheduling, more important tasks get CPU access first. Free RTOS is highly portable, supporting 35 plus hardware architecture, making it an excellent choice for embedded systems and IoT applications. The history of FreeRTOS. FreeRTOS was first developed by Richard Berry in 2003 under a company called Real-Time Engineers Limited. In 2017, it was acquired by Amazon Web Services, which helped accelerate its development and integration with cloud services. Over the years, FreeRTOS has seen steady growth, with nearly 100 versions released so far. The FreeRTOS community plays an important role in shaping its roadmap, especially after 2017, with growing focus on AWS2 integration. The latest version includes new features like symmetric multiprocessing support, improved multi-protection unit, stream batching buffers, and better tracing and security enhancements. Goals and purpose of FreeRTOS. FreeRTOS was built with embedded systems in mind, especially those with limited memory and processing power. It is free and open source, released under the MIT license, which encourages broad usage and modification. The OS is designed to be straightforward, compact, and adaptable. It's written mainly in C, which makes it highly portable across architectures. For task scheduling, FreeRTOS uses multiple priority lists, allowing developers flexibility in how tasks are handled. The project is community driven with active development and feedback via GitHub. Key features also include multi vendor hardware support, works with chips from NXP, TI, and more. Built in communication protocols, a security layer for safe operation, and helpful debugging tools. File system support for persistent storage in embedded services. Standards and platform governing FreeRTOS. FreeRTOS follows real time standards including deterministic task scheduling, priority based preemption, and synchronization tools like semaphores and mutexes to ensure predictable task execution. It is released under the MIT license, making it free to use, modify, and distribute, a key factor behind its widespread adoption in both academic and industry. Amazon FreeRTOS extensions enhance FreeRTOS with features for IoT application such as integration with AWS IoT Core and AWS Greengrass. FreeRTOS is compatible with popular development tools like Visual Studio Code as well as vendor specific IDEs, making it easy to integrate into existing workflows. Lastly, FreeRTOS integrates well with CMSIS, the ARM Cortex microcontroller software interface standard, offering a consistent hardware abstraction layer for ARM based systems. Let's go to the design and implementation of FreeRTOS. FreeRTOS is built on lightweight microkernel optimized for task scheduling and memory management in embedded systems. It supports dynamic priority based scheduling, allowing developers to balance responsive and complexity based on system needs. The microkernel architecture enhances modularity, security, and ease of maintenance. Each component can be developed or updated independently. The core kernel code is compact, about 9,000 lines of C code, mostly contained in two key files, task.c and queue.c. Importantly, FreeRTOS is hardware independent, making it easily portable across a wide range of microcontroller platforms. So there are 5 fundamentals of FreeRTOS. Let's talk about multitasking. Multitasking is a core feature of FreeRTOS, allowing multiple tasks to run concurrently, similar to how it's done in Linux but optimized for microcontrollers. Each task is treated as an independent program, and the scheduler manages when and how the tasks are executed. This structure allows developer to break down complex applications into smaller, more manageable components. Task partitioning brings several benefits. Simplifies testing by isolating functionalities into separate tasks. Enable parallel development, making it easier for teams to work on different parts simultaneously. Encourages code reuse by modularizing functionalities. Most importantly, the OS handles timing and task sequencing, reducing the need for manual control logic and improving system reliability. The second fundamental property is scheduling. FreeRTOS scheduler plays a key role in deciding which task runs and when, ensuring that real-time deadlines are not met. Tasks are permanently assigned to the CPU. They can be suspended and resumed multiple times based on priority and system state. FreeRTOS uses dynamic preemptive priority based scheduling by default. In preemptive mode, the highest priority task always runs, and if two tasks have the same priority, they share the CPU time using the time slicing. In cooperative mode, tasks yield control voluntarily or when they enter a block state, useful for simple or lower power systems. RTOS also addresses priority inversion, a situation where low priority tasks block high priority ones, using non blocking techniques and timeouts to reduce locking issues and maintaining system responsiveness. Let's go to context switching. Context switching is a fundamental part of multitasking in RTOS. A task execution context includes data like CPU registers, stack contents, and access to RAM or ROM. When one task is suspended, another task takes over. It may modify processor states. That's where the FreeRTOS kernel comes in. It saves the full context of a task before switching it out and restores it exactly when the task resumes. This ensures that tasks pick up right when and where they left off without any data corruption or logical errors. Context switching is a process of saving and restoring the task's execution state to enable smooth multitasking. So let's go and talk about the coroutines, which is the fourth fundamental property of FreeRTOS. Starting with version 4.0, coroutines were introduced as a lightweight alternative to tasks, especially useful in systems with tight memory constraints. Key difference: coroutines share a single stack, which helps drastically reduce our RAM usage, a big advantage in embedded applications. Scheduling wise, coroutines uses cooperative scheduling. They yield control manually, unlike tasks which are often preemptive scheduled. Interestingly, tasks and coroutines can coexist, enabling a hybrid scheduling model for added flexibility. Coroutines are implemented using macros, making them easy to integrate without modifying the kernel. But this also introduces limitations. They can't perform blocking operations and have restricted control flow. So they are not suitable for application types, but are perfect for lightweight periodic functions. Uses of queues and semaphores in FreeRTOS. In FreeRTOS, queues are the primary mechanism for inter-task communication. They work by copying items into queue, not by reference. This maintains data integrity but can be inefficient for large data structures. The queue system is implemented in the block queue.c and is accessible from application level code. Both tasks and coroutines can block when waiting to send to receive from a queue, enabling efficient synchronization without CPU waste. Semaphores in FreeRTOS, especially binary semaphores, are implemented using macros built on top of the queue infrastructure. This design avoids redundant logic and takes advantages of the proven reliability for the queue system. Developers can also extend this to counting semaphores depending upon the application's need. For practical reference, the file demonstrates proper usage of semaphores for task signaling and shared resource management. Subcomponents of FreeRTOS and their functions. The FreeRTOS kernel is extremely lightweight, made up of just three main files: list.c, queue.c, and task.c. It continuously manages task scheduling even during the idle time. Scheduler supports both preemptive and round-robin scheduling. In contrast to Linux, FreeRTOS applies just one scheduling strategy system-wide. Inter-task communication is handled through built-in mechanisms like queues, semaphores, and mutexes, which provide simple but effective data exchange and synchronization. Interrupts are hardware specific and handled by the FreeRTOS port for each CPU architecture. This allows precise control based upon the target hardware. Hardware interfaces like serial ports, Wi-Fi, Bluetooth, and Ethernet are supported depending on the hardware and FreeRTOS port used. Security is not part of kernel itself. It must be implemented at the application level, tailored to systems' unique requirements. The complexity and cost implementation in FreeRTOS. FreeRTOS is open source and released under the MIT license, which means it's free to use both in personal and commercial projects without needing to disclose proprietary code. For organizations that need legal assurances or extended support, optional commercial services are available. Why do so many developers adopt FreeRTOS? It supports a wide range of hardware architectures and tools. It's known for being reliable, active maintained, and packed with essential features. Very low resource usage, typically requiring 6K to 12K bytes of RAM or ROM for the kernel. It's also completely unrestricted for commercial use, which encourages wide adoption. Its scalability and lightweight nature make it ideal for resource constrained systems, for smaller IoT devices to industrial grade embedded solutions. The pros and cons of FreeRTOS. Let's talk about pros first. Free and open source, available under the MIT license. FreeRTOS is cost free for both commercial and non commercial use. Highly portable, designed to work across a wide range of microcontrollers and architectures, simplifying cross platform deployment. User friendly API. Its simple, clean API makes it easy to learn and implement, especially for embedded developers. Built in security features offers tools for secure implementation, which are crucial in IoT and network connected devices. Scalable and adaptable. Supports over 60 microcontroller platforms, making it fit for both small embedded devices and large scale IoT systems. Affordable IoT solution. When used with AWS FreeRTOS, it provides a low cost and powerful platform for building the IoT products. Now let's talk about cons. Challenging in complex systems. Managing many concurrent real-time tasks can become error-prone and harder to maintain. Limited OS features. Lacks features like file systems, UI, or advanced networking typically found in full-fledged operating systems. Compatibility issues. Not all hardware platforms or developmental tools integrate seamlessly with FreeRTOS. Learning curve. Developers new to embedded system or real-time design may find FreeRTOS difficult to grasp initially. So companies using FreeRTOS and market insights. FreeRTOS is widely adopted across various industries, supported by many hardware and embedded system vendors. Notable companies using FreeRTOS include Actron Air, Advanced Navigation, Philips, and Prevag Dynamics, spanning industries like electronics, automotive, and navigation systems. The global RTOS market is projected to grow rapidly from 2023 to 2031, with FreeRTOS playing a central role due to its flexibility, open source nature, and wide hardware support. Industry usage breakdown: 16% from information technology and services, 13% from semiconductor sectors, 7% from computer software, 6% from computer hardware. Geometrically, the majority of FreeRTOS clients, 58%, are based in United States, followed by 6% in India. In terms of client size, 50% are large enterprises with revenue over 1 billion, while 31% of small businesses under 50 million, showing how FreeRTOS appeals to both ends of the market. Future trends of FreeRTOS. FreeRTOS continues to grow with nearly 100 versions released and strong industry-wide adoption. A key drive for its success and its active community, developers contribute through forums suggesting new features and fixing bugs, keeping the platform evolving. The latest release, launched in April 2024, introduces several major enhancements. Symmetric multiprocessing allows task distribution across multiple CPU cores using a single free RTOS kernel. Enhanced security, added memory protection unit supports to strengthen memory safety in critical system. Improved tracing tools, enables better debugging and real-time monitoring during the development. Performing improvements, added features like buffer overflow protection, better heap handling, and CMake based build optimizations. Backward compatibility is maintained with versions 10.6, ensuring a smooth upgrade path for existing uh, pre-RTOS users. So, FreeRTOS is powerful, flexible, and widely adopted RTOS, especially well suited for embedded systems and IoT applications. It is rich feature set, broad hardware compatibility, and strong community support, making it ideal solution for developers working on real-time systems. With industries like robotics, automotive, and industrial automation demanding more deterministic and low latency solutions, FreeRTOS is expanding well beyond its traditional roles. Thanks to its scalable architecture, frequent updates, and open source model, FreeRTOS continues to evolve to meet new technological needs. It's clear that FreeRTOS is well positioned to remain a leading RTOS in rapidly growing embedded systems market. So, I'm ending my presentation with the following references. Thank you.